Good afternoon, everybody. Today we're going to look at this cubic polynomial, and we're going to get the first derivative, its second derivative, and we're going to label all of its critical and inflection points. Okay, so let's start off by getting the first derivative. So the derivative function y prime is going to be 3x squared plus 12x plus 11, right? And then a little later on, we'll want to get the second derivative for its inflection points. And so the second derivative is going to be at 6x plus 12. Okay, so first we should probably start by drawing a rough sketch of our original polynomial. Okay, now you could use the rational root theorem, or if you know how to factor in any other way, then you can factor yourselves. But I happen to know, because I made this question, that this cubic polynomial factors into the linear factors x plus 1 times x plus 2 times x plus 3, conveniently enough. Okay, so what that means is that we have a 3 single root polynomial at -3, -2, -1 with a y-intercept at +6, right? So y-intercept all the way up here. And this is a positive cubic polynomial, and so the shape is going to look roughly something like this. Okay, now that's a very rough sketch, and we'll add some details as we go along with the local max, the local mins, and the inflection points. But for now, that'll do for a rough sketch. So to start things off, let's get our critical points. Our critical points, and those are found where the first derivative is equal to 0. Right? They're the ones with a horizontal tangent line, a tangent line to the curve that has a slope of 0, right? Hence why the derivative function has a value of 0. Tangent line has a slope of 0, okay? So for us, that looks like it's going to be this point and that point. So let's find out where those are. Now, setting the derivative function equal to 0 means we're going to set this equal to 0. And this does not look factorable to me. Even by decomposition, 3 times 11 is 33. When it multiplies to 33 and adds to 12, unless I'm going crazy, there are no integer solutions to that question. And so we'll use the quadratic formula. And we'll find that x is going to be -12 plus or minus square root of 12 squared is 144 minus 4 times 3 times 11 all over 2 times 3. Which means that our x coordinates for the critical points are going to be at -12 plus or minus, that's the square root of 144 minus 4 times 3 is 12. 12 times 11 is 132. And finally, 144 minus 132 is just 12. And we have all of that over 6. And so that means that our x values are going to be root 12 is 2 root 3. And so we're going to have -12 plus or minus 2 root 3 all over 6. And that is -2 plus or minus root 3 over 3. And those x values are roughly, root 3 over 3 is roughly 0.57. 0.58, and so -2 minus 0.58, that's going to be roughly -2.58, and the other one, -2 plus roughly 0.58, is going to be at roughly -1.42. And so those 2 points are, this is at roughly -2.58, and this one is roughly at -1.42. Now, we don't know the y-coordinates of those points yet, right? But to get those y-coordinates, we can plug in these x values into our original function. Remember, this is on the original curve described by y, right? And so to get the y-coordinates that are corresponding to these respective x-coordinates, we would have to plug in these x-coordinates back into the original function, right? And we could go ahead and do that. But first, I want to make sure that we label them properly. And so this point here very clearly is going to be a local minimum. And this point here is going to be a local max. Right? Now we know those because we can see it graphically, but it would be nice for us to be able to verify that with something else, like the second derivative. So let's go ahead and do that. The second derivative is going to be 0. So remember, we have our inflection points, or rather, I should say, potential inflection points. Inflection points when the second derivative is equal to 0. So for us, that means setting y double prime, the second derivative, equal to 0. And that means that x is equal to -2, right? And so maybe you can see that. That right there certainly does look like the transition point from a downwards concavity, from a function that is concaving downwards, opening downwards, as it transitions to the point where it starts opening upwards, right? It's transitioning from a downwards concavity to an upward concavity, right? That transition point is that inflection point, right? This right here is our inflection point, okay? And now, if you've studied these curves, you've noticed that we have a local max when the function is, first of all, at a derivative value of 0, so the slope of the tangent line to the curve at that point is 0, and it's concaving downwards, right? If it's concaving downwards, then it looks like a frown, as I tell my students. And so the top of it has to be local max, or that has to be the top of a frown. And conversely, down here, this is concaving up, right? It looks like a smile. And so this point here needs to be the bottom of a smile, right? And so this has to be local min. And so to do that, what we can do is put our x coordinates, our two respective x coordinates, into the second derivative and test to see the sign of that second derivative. A positive second derivative means an upwards, a positive concavity, so an upwards concavity. And conversely, right, a negative second derivative means it's opening down, a negative concavity. Okay, so let's go ahead and test those out. Test for concavity. The first one, let's try to see. We should expect a negative second derivative here, right? We should expect a downwards concavity, meaning this would indeed be a local max. And I haven't butchered our graph completely, right? Let's plug in that x coordinate, negative 2.58, into the second derivative, okay? So the second derivative at x is equal to negative 2.58 is 6 times negative 2.58 plus 12. Again, that's an estimation, 2.58, right? But to one decimal place, two decimal places, that's good enough. And so this is going to be roughly, that's what, that's negative 15.48 plus 12, which is roughly negative 3.48, which is definitely a negative value, obviously. And so that does imply local max at the x is equal to negative 2.58 point, right? And so that looks like it works out. And then we can test in the opposite direction. We can test to see if the point at x is negative 1.42 is indeed a local min, because we should expect a positive second derivative value, right? A positive concavity, because it's concaving up, it's opening up at that point right there, which serves as its local minimum before it ramps back up. And so let's do that over here, maybe. Y double prime when x is negative 1.42 is roughly 6 times negative 1.42 plus 12, which is roughly, what is that? That is negative 8.52 plus 12, which is roughly positive 3.48. Not a coincidence. And so that is obviously a positive value. And so what that means is, since this is a positive second derivative function, this means that we have an upwards concavity, right? Which does confirm that we have a local minimum at x is equal to negative 1.42, right? And so now we have our confirmed local max, confirmed local min. We have our inflection point at x is negative 2. And of course, if we want the y coordinates, we can just plug in each of those x coordinates into the original curve, get the y, and we're done. And so I'll leave that for you guys. It's not super integral to this problem. But again, the first derivative gives us our critical points, which we can test to see whether they are local maxes or local mins. And then the second derivative gives us the concavity of those critical points, which tell us whether we have a local min or a local max based on the concavity. And it also tells us when we set the second derivative equal to 0, it tells us the inflection points. The inflection points, once more, are the points where we transition from a negative concavity to an upwards concavity, right? When the function no longer opens down and begins to open up, or vice versa. Those are our inflection points, okay? And so that's our curve sketching. I really hope this helps. And as always, thanks for watching.